The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin. Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. And when you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them, still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre.
Einstein just could not accept that entanglement worked this way, convincing himself that only the math was weird, not reality. He agreed that entangled particles could exist, but he thought that there was a simpler explanation for why they were linked that did not involve a mysterious long-distance connection. Instead, he insisted that entangled particles were more like a pair of gloves. Imagine someone separates the two gloves, putting each in a case. Then that person delivers one of those cases to me and sends the other case to Antarctica. Thanks. Before I look inside my case, I know that it has either a left hand or a right hand glove. And when I open my case, if I find a left hand glove, then at that instant, I know the case in Antarctica must contain a right-hand glove, even though no one has looked inside. There's nothing mysterious about this. Obviously, by looking inside the case, I've not affected either glove. This case has always had a left-hand glove, and the one in Antarctica has always had a right-hand glove. That was set from the moment the gloves were separated and packed away. Now, Einstein thought that exactly the same idea applies to entangled particles. Whatever configuration the electrons are in must have been fully determined from the moment that they flew apart. So, who was right? Bohr, who championed the equations that said that particles were like spinning wheels that could immediately link their random results even across great distances, or Einstein, who believed there was no spooky connection, but instead, everything was decided well before you looked. Well, the big challenge in figuring out who is right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Bohr would say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality. In 1967, at Columbia University, Einstein's mission to challenge quantum mechanics was taken up by an unlikely recruit. John Clauser was on the verge of earning a PhD in astrophysics. The only thing standing in his way was his grade in quantum mechanics.
When I was still a graduate student, try as I might, I could not understand quantum mechanics.
Clauser was wondering if Einstein might be right when he made a life-altering discovery. It was an obscure paper by a little-known Irish physicist named John Bell. Amazingly, Bell seemed to have found a way to break the deadlock between Einstein and Bohr and show once and for all who was right about the universe.
I was convinced that the quantum mechanical view was probably wrong.
Reading the paper, Clauser saw that Bell had discovered how to tell if entangled particles were really communicating through spooky action, like matching spinning wheels, or if there was nothing spooky at all, and the particles were already set in their ways, like a pair of gloves. What's more, with some clever mathematics, Bell showed that if spooky action were not at work, then quantum mechanics wasn't merely incomplete, as Einstein thought. It was wrong.
I came to the conclusion that, my God, this is one of the most profound results I've ever seen.
Bell was a theorist, but his paper showed that the question could be decided if you could build a machine that created and compared many pairs of entangled particles.
Bell turned the question into an experimental question.
It wasn't just going to be about philosophy or trading pieces of paper.
And the experiment that he envisioned could be done.
You could really set up an actual experiment to force the issue.
Clauser set about constructing a machine that would finally settle the debate.
Now, I was just this punk graduate student at the time. This really seemed like, wow. There's always the slim chance that you will find a result that will shake the world.
Clauser's machine could measure thousands of pairs of entangled particles and compare their spins in many different directions. As the results started coming in, Clauser was surprised and not happy.
I kept asking myself, what have I done wrong? What mistakes have I made in this?
Clauser repeated his experiments, and soon French physicist Alain Aspect developed a more sophisticated test. With significantly more definitive results, Aspect removed virtually all lingering doubt. Clauser's and Aspect's results are truly shocking. They prove that the math of quantum mechanics is right. Entanglement is real. Quantum particles can be linked across space. Measuring one thing can in fact instantly affect its distant partner, as if the space between them didn't even exist. The one thing that Einstein thought was impossible, spooky action at a distance, actually happens.
I was, again, very saddened that I had not overthrown quantum mechanics, because I still had, and to this day, still have great difficulty in understanding it.
That is the most bizarre thing of quantum mechanics. It is impossible to even comprehend. Don't even ask me why. Don't ask me which you're going to, how it works, because it's an illegal question. All we can say is that is apparently the way the world ticks.